great session. It's a great pleasure to introduce Christoph Thiele from Bonn. He's on a short but very efficient visit here to Lisbon. We are very happy to have him, and he will talk about quantum signal processing and nonlinear Fourier analysis.
Yeah, thank you, Diogo. Thank you for the invitation to speak here. I'll be talking about quantum signal processing and nonlinear Fourier analysis, which is joint work with Michel Alexis and Georg Nazarkadze at Bonn. And it's about a story that started this summer at a conference at ICERM on applied harmonic analysis. And there was a talk by Lin, who was telling about quantum signal processing, and I didn't know much about quantum signal processing at the time, but I realized during the talk, well, it sounded somewhat familiar, so over the summer, we were able to make the connection between quantum signal processing and nonlinear Fourier analysis, which is something we've done for a while. So what is quantum signal processing? So let's do the following. Let's look at the sphere. So quantum is about unitary matrices. So we'll be talking about SU2. And the SU2 is a double cover of the rotation group in R3. So let's look at the rotation in R3 for simplicity. That's where it's easier to draw pictures. And so we'll take a vector, North Pole say, and then we will alternatingly rotate it. So we'll rotate it around this axis. So we'll be rotating it this way by some amount. And then we will rotate it around this axis. So we'll be rotating it like this. And then we'll just alternate these rotations. And we are watching what's happening to this vector as we rotate the sphere around. And in the end of the day, the vector will be somewhere, and we'll be looking back the projection onto this vertical axis, so we get a point. And now what do we want this point to be? Well, we want, one of these two rotations should always be the same and have a parameter theta in it, how much we rotate. And the other rotation, the other direction, comes with a certain angle, and I use this angle as free parameter. So I have a sequence of free parameters. And what I like to do, in the end, what I get is a function in this theta. So the point, the height, in the end, is a function of this theta. And I would like to represent any function. My favorite function I like to represent by tuning these parameters suitably. So let me write down a few things. So there is x. These are two Pauli matrices, and they have to do more with SU2 than with rotation, but never mind. 1, 0, minus 1. So we will do the following: e to the I, say psi 1 times z. So this is, you should think of this as a rotation in one direction by this parameter epsilon. This is just making it a matrix. And then you do e to the I theta x. This is the rotation in the other direction. And then you do e to the I theta 2 z back in the first direction, but with second tuning parameter. And then you go again e to the I theta x, and so on. Say a finite sequence, or you could try infinite sequences. And then this is going to be a 2 by 2 matrix. And there's going to be a phi of theta up here, which also depends on the sequence psi, but here I care about. In fact, I don't even care about the other entries of this matrix. And so here's a function under suitable symmetry assumption on this P will actually automatically be a purely imaginary, if you wish, function. So really, this is about having an interval theta and given any function phi of theta, and I'd like to represent this function in such a manner, and that's called quantum, or that's sort of a major part of quantum signal processing. So that's the signal, and processing the signal means representing it in such a fashion. And the question is, which signals can you represent in that way? How do you do it? Given a signal, how do you find size? And what signals anyway can you do? And so I'll leave it like that. So that's really most of what I'll be talking about quantum signal processing. Now let me talk about nonlinear Fourier analysis. Nonlinear Fourier analysis. And then we'll just make the connection. And let me actually go to my notes. So let's recall the Fourier transform on the real line that f of c equals integral r f of x e to the minus 2 pi I x c dx. And it talks, right? So let's see, classical Fourier integral on the real line. And in talks, I like to abbreviate the writing by using that e to the 2 pi I is equal to 1. Okay, so we'll do r f of x 1 to the minus x psi dx. And of course, there is a choice of logarithm in the definition here that has to run properly, but it's just a talk. And here you see, if f is in the space L1 of R, then this integral is in the Lebesgue sense perfectly well defined. So you have a theory of L1. So if f is in L2 of R, then this integral is not well defined, but you have an identity, a Poincaré identity that allows you to upgrade from L1 to L2 function the definition of the Fourier transform. And we'll be seeing something very similar happening here. In fact, that's in a nutshell what we did. The quantum signal people knew how to do this with L1 sequences. And we were able to explain how to do it with L2 sequences by having a suitable nonlinear Poincaré. All right, that's in a nutshell of the story. So let's so far it's linear Fourier analysis, so let's do nonlinear. And so we'd like to view this integral here as a process. And that's so how this like a process as follows. We define the partial sums, the integral from minus infinity to x, f of t equals 1 to the minus t c dt. So now we have a very similar integral, but now we have this upper limit as a parameter, and it's a process as x moves from minus infinity to plus infinity. We are completing the Fourier integral, so to speak. And this can be expressed by an ODE. So we take the partial derivative of this, while taking the partial derivative in x, this gives me the integral of x 1 to the minus xc. And at minus infinity, the 0, right? And at plus infinity, we are f hat of t. And again, if f is in L1, whatever may be required to have solutions of this initial value problem can be justified. So, given this ODE, I can do things with f. For example, I can exponentiate. I can write g f equal e to the sf. I just want to turn this, which is something of an additive process, into a multiplicative process, or an exponential turning addition into multiplication. So then what is the ODE satisfied by e? Well, it's g of gf of x c f of x 1 to the minus xc. This is the exponentiation. It's differentiating this itself times inner derivative. And g GF at C minus infinity equal 1 because e to the 0 is 1. And GF at C plus infinity is e to the f hat of C. So really this is, if you will, this is a point of view, nothing really has happened. We haven't departed very much from the original Fourier integral, just written it differently. So what's the point of writing it multiplicatively? So writing it multiplicatively allows to do matrix value generalizations. We could have G, say, a 2 by 2 matrix, and then we would have to write a 2 by 2 matrix here. At which point, because matrices don't commute, so here the point is scalars commute, so therefore you can take the log and go back. If you put matrices in here, they don't commute, they have no closed form integral of that, so you actually deviate to something completely different. So let's do that. So let's write a matrix OD, dxgf of cx equal gf of cx. So, and there's some choices what you do here. Let's fix a choice today. Let's 1 to the minus xc minus f of x bar 1 to the plus xc, or this is just the bar of this 0. So what are we doing? We're taking this very same functional expression and we embed the complex numbers here into the Lie algebra actually of SU2. So that's a real linear embedding of this complex variety into three-dimensional variety. So we have departed much from what was happening there, but we did want the matrix value, so we did that. And then G of C minus infinity is the identity, parallel to how it was over there. And GF of C infinity is what we would like to call the nonlinear Fourier transform. And it's a matrix, and in fact it will be a matrix of this form. Anyhow you want to see it, the abstract way to see it is that that's an element in the Lie algebra group SU2, so we expect this to be an ODE on the group SU2. You can also just abstractly write down, you can write down an arbitrary matrix, write some equations for that using the ODE and realize the matrix has to look like that. In particular, also A squared plus B squared equal to 1. The determinant is 1 because the trace here is 0. The determinant here has to stay 1. So this is the group SU2, the group of unitary matrices, 2 by 2 matrices with determinant 1. So we have made a definition of a nonlinear Fourier transform, and now you can ask some questions. And let me do a little bit of the theory here. We will be more interested in the pendant of this for series rather than for functions. But the integral, the equations look a little bit more smooth in the integral sense. So how can you solve this ODE? There's one way of doing it, it's called Picard iteration. So you make a sequence of approximations, say G0. G0 is 1, 0, 0, 1, the first approximation. And then, you turn this differential equation into an integral equation, and then you iterate. So G, K, F of C, X equal 1, 0, 0, 1 plus integral minus infinity to x gk minus 1 f of ct 0 f of t1 to the minus tc f of t1 to the minus tc complex conjugate 0 minus. And it's going to be easier if I call this tk. So that will be harder to read. tk. So you recognize, turn this differential equation, integrate this initial condition at minus infinity is identity, and then you integrate from minus infinity to x the derivative, which is this. And since you don't know yet what g is, you take your last approximation of g, put it in here, and that's your next step. And because integrations is not an operator, this is actually something that you do want to iterate. So then the limit as k goes to infinity will be not in a Fourier transform. Well, in particular, let's actually see what we can say about f being in L1. All right, so if f in L1, we should have all the formulas I'm writing down should be all well defined and make sense. So let's do f in L1. So turns out dk minus gk minus 1. So the difference, if I take the difference of two of those, this will fall out. And I just have the integrals of the difference, the previous difference, and then I can write down, I can sort of do this iteration and just multiply out and do this. So this of cx is integral, and let's do it infinity right away. T1 less, etc. less than tk. All right, so if you want to evaluate this, you have to integrate the previous from over tk minus 1 going all the way to tk. So tk minus 1 is less than tk. So only if you iterate, and then you get this product 0 f of t1, 1 to the minus t1c, and then so on. And here is the complex conjugate f of tk, 1 to the minus tk, and you integrate over all the variables. And so this is a multilinear term in f. It's real multilinear as f bar down here. So the multilinear term in f. So this gk automatically comes with the multilinear expansion, just like with the telescope. Each of these you know what the multilinear term is. So you have a chance of this being an analytic map in f if you have the Taylor theorem. This is a Taylor theorem expansion in f. If all the terms, if all these integrals are well defined, we'll have an analytic map. So let's do some estimates. Let's do gk minus gk minus 1. Let's estimate. Let's estimate this in operator norm. So we put the operator norm inside, we estimate the operator norm of such a matrix is just the absolute value of what's written here. So it's more or less equal to integral t1 less etc. less than tk, and you do f of t1. This one has modulus magnitude appears f of tk. And now you realize this is the only this is where interesting constraints happen. You could permute. If you sum of all permutations of this order of these tks, you will be integrating over the whole rk, at which point this will be just separating the integrals. You get one norm to the k. But since this was over summing over all symmetrized versions, you get this. So you realize if f is an L1, these multilinear terms are very, very small. In fact, this 1 over k factorial should remind you of the exponential series. In fact, that's where we came from the exponential. So it's closely related. So you see, for f in L1, these multilinear terms decay sufficiently rapidly for this to be summable for any L1 norm of f. So this is an analytic map on L1. Everything is good on L1. And now there is, in particular, we've got this. You can sum these estimates over k, and you get a nice estimate. The L infinity norm of the Fourier transform is small, when the L1 norm of f is small. Now that the L infinity norm is bound is maybe not so interesting in view of this identity here, but for small f, the L infinity norm here will be small. Now there's something that actually I'm not sure, Diogo, you can tell me whether you knew that. We know actually more about the range of the map. If f is in L1, these guys are not just in L infinity, but they are the Wiener space A. You know that? I learned it from the quantum, because that's what the quantum
for me to say I didn't know.
So that's it's a two-line argument. So that's I wanted to share, because that's actually something I learned. So that's what the quantum sigma people did. They studied the range of this map in the Wiener space. So what's the Wiener space? The Wiener space, you want to say this as a function in C is the Fourier transform of an L1 function. This would be more precise information than saying this is a bounded function. So what do? We take the inverse Fourier transform of this, and we check whether it's an L1. So let's take the inverse Fourier transform of this, dk minus gk minus 1 of c, 1 with cy c. This is the inverse Fourier transform. Here's again my convention. And this is equal, so let's plug this in. And now we have to do slightly, let's divide what comes out. We have to do slightly more precise than the above calculation, but not terribly much. 1 to the c times y minus t1 plus t2 minus and then f of t1, f of t2 bar, etc. And that's what it is. And then in the end, dc. Of course, all the dt's, and then in the end, dc as well. So what's happening? Well, now we have to, rather than estimating each matrix, we just have to take the products, because they're off diagonal, we alternating between the upper and the lower entry when we take these products. So you're getting this, and let's just leave it like that, and we'll try to check the plus or minus signs here. So now this is, if we do the integral in C, we see only this is integrated with C, it's a pure exponential, gives me the Dirac delta of what's here. And let me do T1 less than Tk, so we get the Dirac delta of y minus T1 plus T2, etc. And I do smaller equal, because once this is the Dirac delta, which is a positive quantity, unlike this thing, I can take absolute values f of T1, etc. f of Tk, and I no longer have the integral dc. Now I just have to, so this is the inverse Fourier transform expression for one of the entries, okay, one of the entries of this product. Now I have to integrate this in this positive quantity in y to check the L1 norm, and you realize, well, if you integrate the Dirac delta in y, you just get 1. And then you're left with the same integral we had up here. So this is more than the 1 over k factorial. Yes, 1 to the day. So very same bound in the end, but for this more precise information in the Wiener space. So you can. So the nonlinear Fourier transform of an L1 function has entries here which itself are linear Fourier transform of some other L1 function.
So here you were also integrating in one.
In the end, that's right. In the end, okay. So integral dy is more than minus. Thank you. this has been used by the quantum signal people. They have used analyticity of this map to near the origin have some bounds of what the map does. We know that it's locally bijective if it's analytic. So now I'd like to pass to Fourier series rather than Fourier integrals. So let's do. So I would like to have not a function f on the real line, but I'd like to have a sequence of numbers on z. And we expect that the Fourier transform of such a thing should live on the circle, which I call T. So for z in T, so this is the set of complex numbers of modulus 1. I define, rather than an ODE, I do a sort of difference equation. So this is g n minus 1 of d 1 over square root 1 plus fn squared 1 fn z to the n fn z to the n bar 1, which on the torus this is d to the minus n. All right, that's you can write this either way you want, and I want g minus infinity, that is v equals the identity matrix, and g plus infinity of d I want to be a, b minus b, and instead of bar I write star. So star is the following: a star of v equal complex conjugate a of v complex conjugate inverse. On torus, it's just a fancy way of writing the complex conjugation, because on the torus, z bar inverse equals z. But the advantage of this starring rather than barring is that the star preserves holomorphicity, because we bar the z twice, we come back to something holomorphic, it's not anti-holomorphic. It's a minor point, let me just stick to it. In fact, if you look at, you see, you find myself writing always these matrices, and because the second row contains no information, I'm writing only the first row. Let's just make a formal thing out of this, let's just identify this in the row. And each time I write, this is in quotation marks, or maybe each time I write a row vector, I mean a matrix of this point. Okay, so I did it already here. I just don't want to do dots anymore. I just write the row. The first row. All right, and so you may wonder why this particular matrix. Well, first of all, we no longer have a difference equation, but we have a product. So better these matrices themselves are in SU2. Previously, the thing with the zeros over here was not an SU2, was the Lie algebra of SU2. Now we need something actually in the group. All right, so this has determinant 1, as you can check on the torus. So then also, and then this is just an equation saying we're just taking a product, an ordered product of these matrices, right? Each time we have a new n, we multiply another matrix. So from this differential product, we have arrived at an actual discrete product. And why this? I did want to share this calculation here, just for the fun. So again, this means a matrix where there's f bar down here. Say f just a number now. So what is that? I want to say if you exponentiate what I previously had. So previously I had this, and I'll ignore this power. Of course, it is e to the I. 2 pi I, this real, this is an element on the circle, and this is an element on the circle, and the n corresponds to the xi, so both are more or less the same. So if I exponentiate this one over here, I claim I get this. So let me do this calculation really quickly. So how do you do expo this? You do the Taylor expansion. You have f minus f bar if you square this matrix, you get a diagonal matrix with minus mod f squared here, which is the scalar multiple of the identity matrix. And we know how to take Taylor series of scalars. So you get the even power sitting here, and with the minus sign of every second term, that's a cosine. So you get cosine of mod f on the diagonal. Here, now, if you take higher powers, whatever power of mod f comes here goes over here. So you have one power of f and then absolute. So let's write like this. Let's correct for the, because one power of the mod will be missing because there's one without the mod. So let's divide by mod, multiply by mod, and you have the correct power. So you get the sign here. You get all the odd terms of the normal exponential. Right? And so on. All right. Now I'm using this convention. So now let's, but we want to write it, basically we want to write it in this form, so we just divide out by the cosine. So that's 1 over cosine, which by the way, which is square root 1 plus tangent squared, this is the cosine. And then we get 1, and here we divide by cosine, so we get f over f bar tangent of mod f, and so on, and then we just call this thing, and then we have the set. All right, let me just be quick. This is not the crucial calculation here. I just want to basically we need a two-dimensional. I mean, we have a two-dimensional. Fn is a complex number with a two-dimensional manifold. We have to embed this manifold in the natural way into the Lie group, which is three-dimensional. We choose this embedding, which is naturally coming from the choice we had before. That's all. Indeed, this nonlinear Fourier series here is exactly to the nonlinear Fourier transform if your function is a bunch of Dirac deltas and the integers. Okay, that's so that on the side. So let's write A and B n. It would be the nth matrix here, and it's just the product. Well, first of all, product k equals 0 to n 1 plus f k squared to the minus r. This is just collecting the scalar factors all up front. And then I'm left with this product 1 f0 and then 1 fn z to the n. It's just collecting the factors in the correct order and finding the first row. And one thing we see, something that I didn't say earlier, but well, we expect, and it's true that this is again analytic for summable sequences, and in fact, we can actually write down the Taylor expansion. We wrote it. So, what is the Taylor expansion? So, anyway, in the first up to first order. Let's just compute one more time the Taylor expansion up to first order in F. So this whole business here is quadratic in F to begin with. So for first order computation, you can ignore this. Well, here on the diagonal, there's one term which is multiplying the ones together. Which is 1. And then everyone else on the diagonal has to go off diagonal and then come back. So there's 2 F's. It's again quadratic in F. It's like the diagonal ones are the even orders. So there's only zeroth order, and if we only care up to first order, there's nothing else. And here on the off diagonal is basically out of this product, you pick ones and F, and all the other times you pick a 1. So what you get is sum k equals 0 to n f z to the k. So the first order approximation This B is just the linear Fourier series, and A in first approximation is just the dot. All right. Well, that's what you see out of this formula, and now let's see how this relates to quantum signal processes. So we do this product here. Right? We will not do much with this product, so let's just keep it. Let's do the following. 1 F0. And so here, 1 F1. And I'm supposed to put Z to the 1 here, but I don't. I do it differently. I write Z to the 1/2, 0 here, and this means 0 Z to the -1/2, and I put Z to the -1/2, 0 here. So these are two diagonal matrices. This entry gets multiplied by this and this, which is 1. And this gets multiplied by this and what's down here, which is the star of this, which is Z to the +1/2. So this gets multiplied by Z. And because all matrices in SU2. So let's do the same thing for the next one, Z to the Z to the +2/2. 0, sorry, I'm writing, I should just write those here. And divide them into 1 F2, and then Z to the -2/2, 0. I'm just doing the same thing here. Okay. And now I notice I can cancel. This -1/2 + 2/2, so I'm balancing a half of it, and that's actually two derivatives, -2/2 + 3/2. So I get the scalar from it, and then I get 1 F0, then Z to the 1/2, 0, 1 F1, Z to the 1/2, 0, 1 F2, and so on. And then in the end, I have 1 Fn, and in the end, the thing doesn't have Z to the -n/2, 0. And now you realize this has the same structure as our quantum signal processing earlier. So this is simply, well, if Z is e to the 2πi theta, say, then this will be, and this half, by the way, is a formula half. Don't sweat too much about the half having two values, as long as you pick the same value everywhere. It doesn't matter which of the two values you pick. But here you do e to the, so this is basically e to the I pi theta. Pi theta is half of 2π theta times 1 minus 1. All right, it's a diagonal matrix, so it's exponential of a diagonal matrix. And this is purely imaginary. The complex conjugate is minus that. So this is of the correct form. That's that. And this one is e to the I. If f is real, f0 times 0, 1, 1, 0. And that computation, that's why I did it here. It's more or less this computation. All right. And, that's what we did here. Okay. So 1, 1. All right. And there's a business about. So the analogy will be better if f is either real or imaginary. If f is real or imaginary, you can decide. If f is purely imaginary, it's if, at which point it's a multiple of 1, 1, which is what I chose here. So I put a purely imaginary thing, which is makes f0 purely real. So you see exactly, and then this just alternates, and you see exactly what we had before, except the role of the two Pauli matrices was the other way around. So we were seeing the quantum signal process, and we were supposed to say it's that we would have to make the transition between the two Pauli. Now, of course, all the Pauli matrices are pretty much equivalent. It doesn't matter which you do. It's just looking at the SU2 from a different angle.
What do you mean by Pauli matrix?
The Pauli, that's the three Pauli matrices.
Pauli.
The biggest which was the quantum feature, all right? It's a quantum SU2. These are generators for SU2, yes, or for the Lie algebra, or I forgot whether it's. Yeah. Anyway, so I will leave it like that. So except for these ornaments here, the quantum signal processing is nothing but the nonlinear Fourier series. For the SU2 model, so the Diogo will know that we have been working a lot on the SU11 model, which is you can put a different, and I did it actually wrong here, I think I put a minus sign here. You can put a minus sign or a plus sign here. If you want to be in SU2, you have to put a minus sign. If you put a plus sign, you're in the other league with SU11. And sorry for doing it wrong in the first place. But that's the model, and it's SU2 because quantum is unitary. All right, so it's unitary SU2, SU11. I would like then, so this was basically the discovery, so coming from this talk of Lisbon, and we talked a lot about quantum signal processing, and there were further nonlinear change of variables. He was talking a lot about Chebyshev polynomials, which in the end is just passing from between theta, cosine theta, theta, and things like that. After all the change of variables, it just turns out this thing, which I should say that the PhD student of mine who in 2003 wrote a thesis, and she studied this nonlinear Fourier series in detail. I'll tell you some of the highlights of that, hopefully, in the remaining few minutes. So one thing, actually, in fact, this expression is by no means new, actually. It goes by the name of layer stripping, for those that have heard it. And it's useful in the sense we can actually say a few more things about A. For AN is the product, and then I claim AN is a polynomial in the inverse. How do you see that? Well, here, whatever you do in this product, you get certainly a polynomial in this z to the 1/2 or 1, so you get, but then in the end you do z to the minus n/2. And so if you put plus 1/2 each time, the minus n/2 cancels all of them, so we have a constant term. If you ever do a z to the minus 1/2 in this product, you will go negative and all the way to minus n. All right, while similarly, you can do the same thing for p. It turns out, so here you actually know what the first term is, just 1, we observed this earlier. Here you don't know what the first term is, so we call it whatever, delta 0, but delta 1, so plus 1 plus delta, like delta n z to the plus n. So here you simply observe that in the end of the day, you don't multiply by this, but you multiply by z to the plus n/2. So the whole thing gets shifted by z to the plus n to the right, which gives you something where you just multiply. So this is consistent with our early observation that in linear approximation that it's this. So we have, and then so in particular, AN is analytic. Well, BN is analytic in the disk. In the disk, this is a set of complex numbers of modulos less than 1. This is all right. So this is the polynomial. So it's analytic in D, and this one is analytic in D star, which is just replacing this Z by Z inverse. Okay, so this is the disk at infinity. Look at the Riemann sphere. And in fact, AN at infinity equal the product k equal 1, k equals 0 to n 1 plus k squared to the minus 1/2. It's just this factor times 1. So which is talking infinity here, so making all these guys 0. So So now the question is this, so the question is that these are finite sequences, now we'd like to take a limit as n goes to infinity, all right? And the question is, does it converge? Now, if the sequence f is summable, we can do something as we did before. The whole thing will be very easily convergent and so on. Now, if you take a square summable sequence, and that's what, again, what the quantum sequence people have lots of insights on. If you take square sum, they have also done some square sum of things. I should not discuss it, but I hope to get to the point where we have some extra insight. So, how do you take a limit? And you don't expect that the limit, for example, will be a pointwise limit, because that's not even true with the linear setting. So here you need some, first of all, you need some space in which you have convergence, and then you need the funny metric, which in the linear case would be the Hilbert space metric. So let's say what the space is, and maybe not do the computation. So the space is this. So we take the Hardy space on D star. This is where A lives, cross the Hardy space of B. This is where B lives. And we do the following metric. So we need distance of 2 points. We need it to be a metric space to have a convergence. So we take 2 points. And we have to define, and it's this. It's the L2 A minus A prime squared to the 1/2. This is the L2 norm of the difference of A. It may be the expected term. This is maybe also an expected term. But then there's another maybe surprising term, which is log of A of infinity minus log A prime of infinity. Absolutely. Well, that's a distance, and it's part of this metric rho. And I claim in this metric, the sequence will converge. And the way to prove it is as follows. First of all, well, let me just sketch the proof. And so you see some non-trivial complex analysis. So you want to show that your sequence as n goes to infinity. First of all, one thing you should note is that if f is square summable, this product is convergent, right? That's exactly what you have to do to check convergence of product, so that makes sense. And so what you do, you want to show the sequence is Cauchy, so you take A and Bn, and you take A and Bn, two different terms. And then you know that the difference is, say this is further out, and the difference is we take this, we multiply a few more matrices, and we get this. And this is all Z, this is F0 to Fn, this is Fn plus 1 to Fn, and this is F0 to Fn. Now, if you believe this formula, and we have seen that, you immediately see that despite that you have the following, you have An of infinity times C of infinity equal An of infinity. Maybe a little bit surprising, because if you actually take this product, you get An times C, but you also get Bn times D star. But Bn times D star vanishes at infinity, so you get this identity, but you can also see this identity quickly from using this identity and just observing these are scalar products. But so now if Fk is square summable, then this is Cauchy, so the C will be small. C at infinity, C at infinity will be close to 1. Or log C infinity will be close to 0. So the difference between the logs is the log of that, which is close to 0. So that's why this converges. All right. Now, in order to see that this converges, you have to bootstrap from that information actually. So here, maybe just a super quick sketch. Well, what you have to do is you have to show that C minus 1 squared goes to 0. As n and n gets large, okay, and then you can do something. And the way you do it is, when you write this as the real part, C minus 1 squared plus imaginary part C minus 1 squared. And then you use that C has an analytic extension to the outside disk to say that this is actually the Hilbert transform of that. So you really don't have to bound this, you only have to bound this. Now what's here there? Well, C as modulus less than 1, so this is really less than integral real 1 minus C, if you wish. This is a number between 0 and 2, and dropping a square just gives you 2. And now this is less than 2 integral, well, now this has an analytic extension, so this is actually 1 minus C at infinity. This is a mean value theorem. And now this is less than, now this is just Taylor expansion, less than 2 minus log C at infinity. And then you use again that log C goes to 0. So that's roughly how you do it, that's not it. But we need some serious complex analysis. You need the mean value theorem along the way, you need the boundedness of the Hilbert transform along the way. So that's, it's not just, you know, something has to happen. So that's, so now we have convergence. And I will maybe drop something. Say, make it faster to the point. So it turns out we have convergence in some space. In fact, we can completely characterize the image, and the image, I haven't written down the image. It's a bit, but small starting point compared to SU11, where this was low previously, but Yajun has luckily characterized this image very properly for us. And I'm not going to write it down, but now what do you do? What we really want to do, we were doing sort of a half line. We started F0, and then we went Fn. And the question is, how do you define the Fourier transform for the full line? So you have F minus 1 before. And really the way to do it, you want to end up with a data like this. And the way to do it is just bootstrap from what you already know. So you cut this in the middle, you look at this sequence and you look at this sequence, and then you say, I understood the Fourier transform of this sequence, and I understand the Fourier transform of this sequence by doing the same to reflect this symmetry. No new theory, just the same. So I can take, so call this part here F minus, and F minus goes all the way to minus 1, so the zeros have to decide where it goes, so it goes to F plus. So I'm getting Fourier transforms, oops, plus. So far for the forward map, we know exactly what these spaces are. We just take product and we can define the space of products, and that's very simple. Actually, is it? Well, okay, so that's what it is. And the hard part is, if you remember, the quantum signal people really wanted to do the inverse. So suppose you're giving this, how do you get back the sequence? So we have to, not, this is just about the forward. Given the sequence, we can define this by taking this product. How do you go back? And that's, I think, which I think has not been observed in the QSP community, but has been observed, maybe also not for SU2, or I don't know, the literature is vast and I don't see all of it. We didn't observe it for SU2. We observed it for SU11, and then to do it for SU2, you have to be a bit tricky, and let me write down what you do. So you're given AB, and you want to know this, and it seems underdetermined, but it's like a Hardy space decomposition. You get a function L2, you want to decompose in Hardy space, anti-Hardy space. It's actually well defined, even though you need 2 out of 1, but it's because we know one has analyticity property in the disk, and the other one has analyticity property in the opposite disk. So it's actually generically a well-defined problem to split such a thing into this, and the way to do it is first you multiply by the inverse of the line, which is A plus star minus B plus. This is the inverse of this matrix. And let's look at the first entry of this. So A A plus star plus B, B plus star equal A minus. So let's divide by A. So now the thing you have to do in SU2, you cannot do it for anything you would like to, but you have to make an assumption that B squared is less than a half and A squared is bigger than a half. We know the sum of both is 1, and we want that A wins. And we not only want that A wins on the torus, but we want that A is larger than a half everywhere on the outside. This is called an outer function. So let's just assume we have this everywhere where A is analytic. So we can divide by A. B over A, B plus star equals A minus over A. And now, here, people do have analytic extension. This is an equation on the torus, but people have extensions either to D or D star. Let's project down to D. So this is the projection in L2, the linear projection L2 on the torus to the Hardy space of functions, analytic extension in D. So what's happening? This one actually has extension to D star, so this becomes a constant. So it's A minus of infinity divided by A of infinity, which incidentally is 1 over A plus of infinity. And here you don't know much, so you just write down what we do. B plus star. And here, this one, A goes to D star, but A star goes to D. So this is actually, nothing is happening to this, it just stays alone. And a similar equation for B. Okay, B, let me just copy B, minus B plus equal PB, B over A plus equals 0. So in this case, you actually get 0. Here you get a constant, you get a 0 constant. So you realize this is, it looks like a fixed point equation. If you put this A plus B plus on one side and these operators on the other side, and you ignore the constant for the time B, you see a fixed point iteration map. You take this A plus B plus, you multiply by B over A. And thanks to that, that's multiplying by a number less than 1. That's a contraction map in L2 space. And then you apply the Cauchy projection operator, which is also bounded in L2 of norm 1. So the operation, so you've got AB, A plus B plus equals T, A plus B plus for some operator T plus constant, and T is a contraction mapping. We just iterate T by the contraction mapping principle, you get a solution for that. And then you see A plus B plus, and then of course you have to compute that. So that's what I believe, the quantum signal people don't have in their literature. It allows you to, well, the way it goes in the end. So the quantum signal people really care about this B, and B should be purely imaginary, so you should have a symmetric sequence. There's no half-line sequence, you want to have a symmetric sequence. And you want to know B, you complement by A, the mod of A is determined by B, and A should be out, and so all of A is determined by B. So that uniquely in A, you can get, you apply the fixed point mapping to get these guys, and then you just, then F0 is just something like B plus of 0 divided by A plus star of 0, so you're getting F0. And if you know how to get F0, you know how to get it. You can just shift the sequence. So this allows in the end, so there's an artificial constraint, which is really artificial. You would want B less than 1, but only B less than a half can be done. But any measurable B, any signal, any measurable purely real signal can be represented by the quantum signal algorithm using these rotations. That's the punchline. That's the result. Thank you for your attention. Thank you so much.